Now let's talk about capacitors in circuits, how capacitors can combine together within a circuit in order to do work for us, in order to do work, to move those charges, in order to store energy. Here's an example of like an electronic breadboard, we call it. And these are little resistors here. And the capacitors are these things right here. We're kind of looking at this from above. So these are really tall, skinny kind of cylinders, and these are the capacitors in this circuit. So what do I mean when I talk about a circuit? A circuit is a collection of objects that contain a source of electrical energy. So that source of electrical energy is usually a battery or some power source. And that battery is connected by wires to elements that convert electrical energy to other forms. And those things have some resistance to them. Those are what we call resistors, or those elements within the circuit can store the energy in electric field or magnetic fields for later retrieval. So the thing that's storing the electric field is the capacitor. The thing that stores a magnetic field is called an inductor, and we'll see those later. Here we have a very simple circuit. We've got a power source, let's say a battery here, and it's going to supply current, which is a flow of electrons to this circuit. We've got a little switch here. Once we close that switch, we close the circuit, and then current can flow through this circuit. Here's our resistors, and here we have a capacitor. We're going to represent resistors as these kind of zigzag wiggly lines here. Resistors are things that resist the flow of current, the flow of electrons or electricity. In capacitors, we represent as these parallel lines like this, and they are the things that are storing electrical energy. Now we can arrange our resistors or capacitors in what we call series or parallel. We say that devices are in series whenever the flow of charge, the current, must flow through all devices sequentially. So here we have 4 resistors. The current has to flow through R1 before it can get to R2, before it can get to R3, and so on. Devices are in parallel whenever each device is connected directly to the power source. But also, maybe an easier way to think about it is that they are in parallel whenever the current coming to those elements has to diverge or get split to multiple branches. So here we have the current that could come through this wire, and it has to split through R1, R2, R3, and R4, and then it has to combine. So those are examples of elements that are in parallel. And we can combine capacitors together in interesting ways. Capacitors are manufactured with many different standard capacitances. By combining capacitors in different ways, any desired value of the capacitance can be obtained. Let's say for some reason you need a non-standard unit for your capacitance in a circuit, and you can't go buy one that's manufactured in that particular capacitance. So you have to arrange your capacitors in a unique way in order to produce a capacitance that could replace that one capacitor that you need. Multiple connections of capacitors act like a single equivalent capacitor. The total capacitance depends on the individual capacitors and how they are connected in series or parallel. So here we have a very complicated set of capacitors. These 2 capacitors are in parallel. These 2 are in parallel with this one in series. And then all along all of these branches, the capacitors along all these branches are in parallel with each other. These 2 capacitors are in series with each other. So you can combine these little components together and make another equivalent capacitor, and you can just keep on combining and combining the elements until you work all your way down to combining all those elements together to represent one capacitor that you could swap out all of those, let's say 6 capacitors with one equivalent capacitance. We have special rules for capacitors that are connected in series and capacitors that are connected in parallel. For a series combination of capacitors, here we have two capacitors in series, the magnitude of the charge is the same on every plate of the capacitor in series. The equivalent capacitance, so the total capacitance of these in series, must end up with the same magnitude of charge on its plates. And we can take these two capacitors and combine them to create an equivalent capacitor, and that's this one down here. So we could replace these two capacitors with what we call the equivalent capacitor, and the equivalent capacitor must end up with the same magnitude of charge on its plates as the magnitude of charge on both of these plates, or I guess there's three plates here, one's behind my image here, that are in series. This equivalent capacitor resembles a single capacitor with an effective plate separation greater than the individual capacitors alone. We saw that whenever the plate separation gets larger, we decrease the capacitance. A larger plate separation means a smaller capacitance. So the equivalent capacitance of a series combination of capacitors is always less than any of the individual capacitances in the combination. And we add them together like this. 1 over the total capacitance of these three in series equals 1 over the capacitance of the first capacitor plus 1 over the capacitance of the second one, and so on. For each of our capacitors in series, the potential across them is equal to the charge on the plates divided by their capacitance. And remember that the charge on all of the plates is the same for all capacitors in series. In series, the potential difference between the terminals of our battery here is the sum of the potential difference across the individual capacitors. So the total potential coming from our battery has to equal the potential across my first capacitor plus the potential across the second plus the potential across the third. And you can replace V with Q over C. So the charge on our plates, which is the same for all of them, divided by the total capacitance equals, we replace V with Q over C, equals Q over C1 plus Q over C2 plus Q over C3. Since all of these capacitors have the same charge on their plates, this Q you could like divide out of the system. And then that leaves us with our relationship for the total capacitance. 1 over the total capacitance equals 1 over C1 plus 1 over C2 plus 1 over C3. For our capacitors in parallel, the capacitors all have the same potential difference across them. It's as if each individual capacitor were connected to the battery alone, the potential of the battery alone. And here's an example of our three capacitors in parallel. They are all supplied with the same potential that comes from the battery. So if our battery has a potential of 5 volts, they all have a potential of 5 volts across their plates. The equivalent capacitor that we could take these three in parallel and replace it with, that's this one down here, resembles a single capacitor with a larger plate area than the individual capacitors alone. When we increase the plate area of the capacitor, we increase the capacitance. So larger plate area means larger capacitance. When we have capacitors in parallel, the total capacitance of those elements is greater than any of the individual capacitances. The equivalent capacitance of a parallel combination of capacitors is greater than any of the individual capacitances. And we can find the total capacitance of our equivalent capacitor that we could replace all these with just by adding up the sum of all the individual capacitances. For each capacitor, the potential difference across them is equal to the charge on that plate divided by the charge on its plates divided by the capacitance. And remember that for all of our capacitors in parallel, the potential across them is the same. So in parallel, the total charge on the plates is the sum of the charges on the plates of each individual capacitor. So the total charge on this big capacitor that we could replace all these individual capacitors with equals the charge on capacitor 1 plus the charge on capacitor 2 plus the charge on capacitor 3. We rearrange this equation. Q is equal to C times V. So this also says that our total capacitance times V equals C1 times V plus C2 times V plus C3 times V. In parallel, all of our capacitors have the same potential difference across them. So this time we can factor out that V, or we could divide that potential and get rid of it on both sides. So that shows us that our total capacitance of the system equals the sum of the capacitances of each individual capacitor. Okay, that was a lot of stuff, right? What does that even mean? We're going to use those rules in order to solve problems where we have 4 capacitors in parallel, and then those same 4 capacitors in series, to see how that changes the total capacitance in our system, the charges that you can get on those plates, and the potential differences across them.
In the next 2 problems, we're going to deal with capacitors in parallel and in series. So I have written down our rules here for capacitors in series and capacitors in parallel. For capacitors in series, the charge on all of our capacitors is the same. The potential across all of them adds up to the total potential in the circuit. And the total capacitance is an inverse relationship. For our capacitors in parallel, the charge adds up throughout the circuit on all of our capacitors to equal the total charge on our equivalent capacitor. The potential difference across all the capacitors is the same, and the capacitance just adds up linearly, it adds up normally for all of the capacitors. And we also have our equation Q is equal to the capacitance times the potential. Q is our charge in our plates. Okay, so we are going to treat a circuit that has 4 capacitors in parallel. These 4 capacitors in parallel are supplied by a battery of 18 volts. Each one of our capacitors, their capacitance is listed here. So our capacitance gets larger as we go down, all right? And so what we have to do is determine the capacitance of the single capacitor that is equivalent to the parallel combination of capacitors. That just means we want to find the total capacitance of this combination of capacitors. That's our first part of the problem, okay? So we have to use our relationship. So when we're in parallel, the capacitance just adds up. The total capacitance in my circuit is going to be the sum of all the individual capacitances for each of the capacitors. So this equation is pretty boring. We've got C total is equal to C1 plus C2 plus C3 plus C4. You just sum up 3 microfarad, 6, 12, and 24 microfarads together. That gives us a total capacitance of 45 microfarads. Easy. And then part B. Find the charge on the 12 microfarad capacitor. So Q, the 12 microfarad capacitor, I was calling 12 microfarads. So let's say we want to find the charge on our third capacitor. So the charge on Q3 is equal to question mark. Okay, this one's a little bit more interesting. To get the charge on our third capacitor, well, that equation is going to be the charge on the capacitor is equal to the capacitance times the potential on that capacitor. So we have to ask ourselves, we know the capacitance of our third capacitor is 12 microfarads, but what is the potential across my third capacitor here? Well, also, this one's a pretty easy one, because when our capacitors are in parallel, the potential across every single capacitor is the same. So every single capacitor is getting a potential across its plates of 18 volts, which is the same potential that's being supplied by the battery to the circuit. So this is just going to equal the capacitance of our third capacitor, which is 12 microfarad, and then we multiply it by the potential across that capacitor, which is the total potential in our circuit supplied by the battery. So that's just 18 volts here. Then the charge on our third plate capacitor is, so we could write this in units of regular farads. But if we take a microfarad times a volt, we will get a unit of microcoulombs. So I can just actually do this multiplication right here without converting anything, and I would get an answer of microcoulombs. Now, if you wanted to get your answer in coulombs, then you would have to write microfarads as 12 times 10 to the minus 6 farads, then multiply it by 18 volts. And in that case, you would get 2.16 times 10 to the minus 4 coulombs for the charge. We could do the same process for the charge on every single one of these capacitors. If we do that for every single one of these capacitors, we sum up the charge on each capacitor. That would be the same as the total charge on this capacitor right here, which is our equivalent capacitor. The one capacitor that we could create that has the same capacitance as these 4 capacitors in parallel. Now we have those same 4 capacitors. This time we're going to place them in parallel with each other. Okay, so when we do that, the first thing we're going to do in this problem is to calculate the capacitance of the equivalent capacitor. That means, what is the capacitance of the capacitor that I could take all of these combination of 4 out and replace it with another capacitor with that same capacitance. So essentially, we have to find the total capacitance of this circuit. That's what we're being asked for. Now, for our capacitors in series, the total capacitance is way more complicated than it is for our capacitors in parallel. In series, we're going to have 1 over our total capacitance equals 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4. Okay, so 1 over C total is equal to 1 over 3 microfarads plus 1 over 6 microfarads plus 1 over 12 microfarads plus 1 over 24 microfarads. Okay, so that's 1 over C total. You calculate all of this, that's 1 over C total. You get this, and you take the inverse of that whole thing, and that gives you C total. So actually I could write like this. C total is equal to all of this stuff raised to the power of minus 1. That's the same thing as taking the reciprocal, is to type it into your calculator and raise it to the minus 1. That's the same thing as saying 1 divided by all of this stuff added together. And if I do that, I find that my total capacitance of this circuit is 1.6 microfarads. So C total for my capacitors in series is 1.6 microfarads. For these exact same capacitors in parallel, we got a total capacitance of 45 microfarads. So we see that in the case where we have the same capacitors, but we place them in series instead of parallel, that the capacitance for the series is much less than the capacitance for my capacitors in parallel. So this is our total capacitance, or the equivalent capacitance, for my circuit here. For our second question, we're going to compute the charge on the 12 microfarad capacitor. Q3 equals question mark for my 12 microfarad capacitor. Now let's see. Q3 is equal to C3 times the potential across it. Now, we know what the capacitance is of our third capacitor, but we don't know the potential difference across it. So how are we going to solve this problem if we don't know the potential difference across my third capacitor? Because the potential difference for our capacitors in series has to sum up. So, well, let's think about it. We have this other statement that says that the charge on all of my capacitors in series is the same. That means that the charge on the equivalent capacitor that I could replace with all 4 of these capacitors has the same charge on it as any one of these individual capacitors. So I could find the total charge on this theoretical capacitor that I could place in to replace all 4 of those in series. So we'll call that Q total. Q total is equal to our total capacitance times the potential. So our entire circuit is being supplied with 18 volts of potential. My total capacitance was 1.6 microfarad times 18 volts. And that gives me a charge for the equivalent capacitor of 28.8 microcoulomb. And so that is the same as the charge on every single one of my capacitors here in series. So this is the same as the charge on my third capacitor. So actually this is how we could answer that question. So we have the charge on Q3 for this problem was 28.8 microcoulomb. For our same problem where our capacitors were in parallel, we found that the charge on Q3 was 216 microcoulombs. So in our capacitors in parallel, we can also pack more charge on them than we can with our capacitors in series. Now for part C, we are asked to find the voltage drop across my capacitor 3, my third capacitor. We want the potential difference across capacitor 3. We know what the charge is on capacitor 3. We know what its capacitance is, so we can use this equation here to get the potential difference across my third capacitor. So I could solve this equation right here for V. V is equal to Q divided by C, so that will equal my 28.8 microcoulomb and divide it by the capacitance of my third capacitor, which was 12 microfarads. Now, if both of these are in units of micro, and I divide them, I'm going to get back units of just volts. Because this is essentially 28.8 times 10 to the minus 6 coulomb divided by 12 times 10 to the minus 6 farads. And these 10 to the minus 6 are going to cancel each other on the top and bottom. So the potential difference across my third capacitor here is 2.4 volts, V3. Now I could go back and I could calculate the potential in this same way across all 4 of my capacitors. And if I add up the potential across all 4 of the capacitors together, they should add up to give me 18 volts, which was the potential supplied by our battery. Because when we have our capacitors in series, the voltage or the potential difference across all of them must add up to give us the potential difference that's supplied by our battery to the entire circuit.